Hello, today's lesson is on 4.1, Discovering Trig. So we're starting our really big unit on trigonometry. First, I want to talk about some review of this thing. So what this actually is it's the Cartesian plane, and we've just got a circle sketched on it. And what we're going to look at in a future lesson is that this circle has a radius of 1, and we call it the unit circle. But it can be any circle. Now, from previous math courses, we know that when we're looking at the Cartesian plane, we always start at the positive x-axis here. This is our 0-degree mark. And as we rotate around the Cartesian plane, we go this way. So we go counterclockwise. And if I happen to rotate from 0 up to the positive y-axis, how far have I gone? 90 degrees. Go another 90 and you end up here at 180 degrees. See what I'm doing? 270, and back at the positive x-axis would give us 360 degrees. So what happens in trigonometry is we end up sketching angles, like I might sketch this angle here, and the angle has a reference angle and an angle in standard position. We're going to define both of those on a future slide. But reference angle goes back to the nearest x-axis, and the angle in standard position always goes back to this positive x-axis that we started at for 0. Now, in this unit, we might talk about some angle theta that we're working with, and it has to be between 0 degrees and let's say 360 degrees. That means it's within one circle around the Cartesian plane. I could also say I want to go between 90 and maybe 180. What something like that is actually telling you is really that you're working within quadrant, let me see, what quadrant 2 here. We're between 90 and 180, so we're in quadrant 2. It's just a fancy trigonometry way of telling you what part of the Cartesian plane we're working in. In Math 30-1, we even go so far as to talk about negative angles and go further than one full circle. So we can talk about a lot of stuff. We'll get to more complex examples like that much later on in the unit. Now I'm including a website here. I'll just show you what it looks like. I'll include it in the email for this week's lesson. And what this website is it's just an explanation of angles, degrees, and radians. Because radians are something we've never worked with before, but we're going to be seeing a lot of in Math 30-1. Degrees we all know about. 360 degrees is a full circle. We're used to working with degrees in previous trig units. But radians are something that are a little more confusing to work with. They include pi. So I've got a reading here that you're going to do to try and understand radians, as well as a YouTube video where a teacher is explaining what radians are. So I'll link that YouTube video as well. Please watch it. He does a really good job of explaining to you where pi comes from and how pi factors into radians. So converting between degrees and radians, what you need to remember is what you want goes on top. So if you want to convert something to degrees, then you have to put degrees on top. If you want to do radians, you have to put the pi on top. So what is this conversion factor? It's pi and 180 degrees. So you're either going to use it in this form or in this form. You're going to pick which one you're using based on what you want. If you want radians, you're going to use this one because pi is on top and radians include pi. If you want your final answer in degrees, you're going to use this conversion factor because degrees is on top. One important thing to note about radians is that they're unitless. Very few times in math do we actually have something without units. And the reason why we're kind of sticklers for you to write the units all the time is because if you're not writing units, what you're really writing is radians. We don't put an R after radians, we don't write rad. It's just something with pi usually that has no units. So let's start with this first column. We want to convert from degrees to radians. So this conversion factor is just something that you're going to multiply by. You're going to multiply by whichever one will change me to radians. Radians have pi, so I'm going to put pi on top. The other way to think about this is the degrees went on the bottom. There's a degree symbol there because top and bottom units will cancel. Now, when we have this, we always want to write it as a fraction. You are not going to put pi in your calculator here. You are simply going to put 270 divided by 180 in your calculator and math frac it. Again, do not hit the pi button. The pi is just going to, come along with us in our answer. But 270 divided by 180 on your calculator should give you 3/2. So the radians for this are 3 pi over 2. Okay, so again, all I'm putting in my calculator are the numbers, and the pi just comes along in my answer on top. Let's try again. Starting in degrees, so for the degrees to cancel, 180 has to go on the bottom, pi has to go on the top. Pi is just going to come along in my answer, and I'm going to put 45 divide 180 into my calculator and math frac it. I get 1/4, which I could write like this if I wanted to, but what's the better way if it's just a secret one? Pi by 4. We know the 1 is there in secret, but we don't need to write it. Pause the video and try the next two. I'm putting pi on top because I want to be in radians. I want my units to cancel. 210 divided by 180, math fract in my calculator, gives me 7/6, and I just pull the pi through. 540 divided by 180, math fract is going to actually give me whole number 3. So 540 degrees is the same as 3 pi radians. Let's try the reverse now. We're starting with something that's unitless. I don't see any units behind 3 pi by 2. I only see a bunch of numbers and a pi. That tells me that this is in radians. So what I want is degrees. That means I have to put 180 degrees on top this time and pi on the bottom. So I'm flipping what I was doing before. What's going to happen with these pi's? You have one on top and one on bottom. They're going to cancel. How will you put this in your calculator? 3 times 180 divided by 2. Now, if you were to omit the degree symbol, you would be 100% wrong. 3 pi by 2 is not 270. It's 270 degrees. Okay, very different. We also have one other way that we can measure angles called gradients that we don't study here, but they do study them a lot over in the UK. And if you look on your calculator where you have degree mode, you also have radian mode and gradient mode on most calculators. Let's do another one. It's in radians, so if I want to go to degrees, I put 180 degrees on top and pi on bottom. I cancel my pi's. I go 5 times 180 divided by 4. Try again. 11 pi by 6. I want to end up in degrees, so I'll put the 180 degrees on top and pi on bottom. Cancel my pi's. 11 times 180 divided by 6. 330. The last one doesn't have a pi in it. This is basically a rounded value, 2.1. It still doesn't have units, so you can assume that it's radians. So I'll multiply with degrees on top, pi on bottom. And this one I'm going to do my equal sign squiggly because I'm just going to approximate and round off some decimals here. It's approximately 120 degrees. Without having that pi in there, it's hard to get an exact value. If it's just a decimal, it's just going to be approximate. Let's review some terminology that we learned last year: reference angles and principal angles. So reference angles, I alluded to these earlier. The definition is how far the terminal arm is from the nearest x-axis. Now this is always an acute angle, which means less than 90 degrees, and it's always positive. We get into negative angles eventually in this unit, but reference angles are always positive, always less than 90. Let me just show you on a Cartesian plane what this would be. If you had an angle, this is your terminal arm. Your reference angle goes from that terminal arm, so put your pencil on the blue line and connect it to the nearest x-axis. Boom. That is your reference angle. It's less than 90. Now, a principal angle is the smallest positive angle. So this means that theta, your principal angle, is between 0 and 360 degrees. Or now that we know radians, it's between 0 radians and 360 degrees would convert to 2 pi. So my principal angle on the drawing that I've already got there goes back to the positive x-axis. It's my angle in standard position that we talked about in grade 11 in the positives. So smallest positive angle here would be something bigger than 90 according to my picture. So maybe it's like 110 degrees. Coterminal angles, if I take that same angle that I have drawn and I swoop this terminal arm around a whole nother time, I add a whole circle to it, it's coterminal. It still terminates in the same quadrant, but it's 360 degrees more. Okay, so the way that we would write this is we would write that it's the principal angle plus 360 degrees a certain number of times. So n is any integer. Now, what is an integer? It's a positive or negative whole number. So I can add a full circle 2 times. That'd be like adding 720 degrees, pardon me. I could add a full circle -1 times. That would actually mean I'm minusing a full circle. So I can go both directions. I can go in the positive direction, or I could go in the negative direction and end up with a negative angle. That's totally possible. If I write this with radians, it's the same idea, principal angle plus 2 pi n. Now remember integers, they're sets of numbers that can either be with an I or a Z. They use both in the textbook, I believe. So let's determine one positive and one negative coterminal angle to the given principal angles. So if I have 120 degrees, let's actually start by sketching this so we all know what this looks like. I'm going to start with my pencil on the positive x-axis because that's 0 degrees. I'm going to go counterclockwise, 90, a little more, That's where my terminal arm is. The blue angle that I've drawn is 120 degrees. I knew that I had to stop before the other x-axis because that would have been 180. So I just drew it somewhere between 90 and 180. All right, that angle is 120, and we want to have something that's coterminal, that's positive. So the easiest way to do that is take 120 and add a full circle. 120 plus 360 would be 480 degrees. If I were to sketch 480 degrees on this same Cartesian plane, it would be the same terminal arm. That arm has just moved around the Cartesian plane an entire full circle more than the blue arm. Now let's go back to that 120. And instead of going in the positive direction, which is actually counterclockwise, I'm going to go in the negative direction, one full circle. So where would that put me? That would start me at 120, negative one full circle, and that's going to give me negative 240 degrees. What is a negative angle? It's just an angle that swoops around the Cartesian plane in the opposite direction. Instead of going counterclockwise, it goes clockwise. Now, if we want to do this in radians, we can do the same thing, but instead of adding and minusing 360 degrees, we're going to add the radian equivalent, which is 2 pi. So we'll practice a lot with radians and we'll get a good idea of where 5 pi by 4 is on the circle. But essentially, you're going to take that angle and you're going to add 2 pi to get a positive and minus 2 pi to get a negative coterminal angle. Now, this is where a lot of math skills over the years kind of pile up into these questions. How am I going to do that without decimals? How do I add fractions so that I don't have to create decimals in my calculator? The easiest way is to make a common denominator. So if I want to make a 4 in this fraction, I need to multiply that top 2 by 4 as well. 8 over 4 is the same as 2 pi. 8 divided by 4 is 2 pi. That's the easiest way to work with radians, is to make common denominators and use your fraction rules. You're treating pi like it's an x. You're just adding like terms. So on the top, I have 5 pi's plus 8 pi's, which is going to be 13 pi's. So just like it was 5x plus 8x is 13x, the pi is just acting like a variable when you add over my common denominator. So flashing back all the way to grade 7, where we needed to know how to add fractions with common denominators. Same thing for subtraction. 5 pi's minus 8 pi's is negative 3 pi's over 4. Now, a lot of people who struggle with a lot of these background skills in Math 30-1 will convert anything in radians to degrees, work with degrees, and then convert back to radians. It shows a weaker skill set, but it is a possibility if you're really struggling to use some of these skills, or if you know that you never really mastered some of these fraction skills, it is a backup plan. So if you want to convert 5 pi over 4 to degrees, add 360 degrees, it's much simpler to do it that way. But I do highly recommend those of you working on your skills so that you can go to post-secondary and use math in your courses, you try and work with the fractions. Another rule that we have to know is if it starts in radians, your answer has to be in radians. Let's write that down nice and big. This is very important. So if you are the person that is struggling with some of your background knowledge and you need to convert to degrees, you need to remember that if it starts in radians, you go back to radians. So if you're doing that method, there's an initial conversion to degrees, then you do your math in degrees, and then you take your answer back to radians. It's a lot of extra steps, whereas just working with the fractions and understanding the rules that we've learned over the years is a little less work, in my opinion. Given the following angles, determine the reference angle now. So we want to figure out that acute angle. It's that angle that touches the closest x-axis. So the best way to see that is with a picture. First, I want you to start with your pencil on the positive x-axis, and I want you to swoop around counterclockwise until you've drawn an angle of about 315 degrees. Here I go. Positive x, I'm at 90, 180, 270. If I get all the way back, I'd be at 360. So I'm going to stop somewhere there in that quadrant. The red angle that I just swooped out in my drawing is 315 degrees. The reference angle. Put your pencil, preferably maybe a different color, on that terminal arm. This is the terminal arm. Put your pencil there and swoop it back to the closest x-axis. Boom. It should be very close most times. That is your reference angle. I'm going to call it theta ref for reference angle. Theta being a Greek capital letter that we use to represent angles that we don't know. Now, using some of your common knowledge about circles, you should be able to find that green angle with a simple subtraction. If I know that a full circle is 360 degrees and the red part is 315, by taking a full circle and subtracting the 315, I should get my reference angle. So for this one, my reference angle is 45 degrees, which sounds about right because it's acute, it's less than 90 degrees. And remember, your reference angles should always be positive numbers. Start with a sketch. Put your pencil on the positive x-axis and swoop around 470 degrees. Well, a full circle is 360, plus 90 is going to be 450, plus a little more is going to be 470. So that blue angle there is my full angle in standard position that I'm talking about. Let's go back first to what the principal angle is. The principal angle is if I take out the extra circles and I just put this terminal arm back to the positive x-axis like that. How big would that be? So I'm going to take 470 and I'm going to minus a full circle to get me back within one circle on the Cartesian plane, which basically puts me back within the math we did in Math 20-1. That gives me an angle of 110 degrees, a little bit easier to work with. Now, 110 degrees going to the nearest nearest x-axis is going to be how far away? Well, this line is 180. This portion we just figured out to be 110. So if I go 180 minus 110, I'll get my reference angle. My reference angle for 470 degrees is 70 degrees. First of all, minusing the extra circle to put me back at a principal angle, and then looking at the Cartesian plane and seeing what kind of subtraction I need to do to get my reference angle to the nearest x-axis. Now, the next one is in radians, and we don't have enough practice yet to know how many radians this is, how far this is on a circle. So we're going to start by thinking in degrees. This is negative 150 degrees, and we'll think through it, and then we can do the calculations in radians. An angle of negative 150 is going to go, instead of counterclockwise, clockwise, but it's still starting on the positive x-axis. It's going to go negative 90, negative 150. It's going to be right there. Now, to get my principal angle, it needs to be positive. So I basically need to move this around a full circle. So it's right back where it is, but in the positive angle. So my principal angle is going to be negative 5 pi by 6, or 150 degrees, plus a full circle, plus 2 pi. What is the trick for dealing with these fractions? I am going to make this have a denominator of 6. So 12 over 6 is 2. Then I'm just going to add the tops. 12 plus negative 5 is going to be positive 7 pi over 6. Now let's think about what we've got here. We've got our angle at 7 pi over 6, our principal angle. And we want to find the reference angle. I'm running out of colors, man. That goes back to the nearest x-axis, just that tiny little blue angle. So if we want to find our reference angle, we want to take our angle in standard position, 7 pi over 6, our principal angle, and we want to do what to find the little blue one? Well, if the entire angle is this green one, I want to take away this top green part here so that I can get this small blue part. I want to take away half a circle. That's 180 degrees. If 2 pi is a full circle, what do you think half a circle is? Pi would be correct. Let's make this pi have a common denominator of 6. And let's subtract the tops. 7 pi's minus 6 is 1 pi's over common denominator. So your reference angle is pi by 6. If you want to do all of that work in degrees and convert it at the end, you can do that, but the more important skill to work on is working with the fractions. If you want to try one on your own, try 5 pi by 3. Now, 5 pi by 3, this is 300 degrees. Since we don't quite know the unit circle yet, we'll start with a sketch of 300 degrees. 300 degrees goes from the positive x-axis all the way around to there. Now, if I want to know the reference angle, first I need to know where it is. It's from the terminal arm, which is this black line, to the nearest x-axis. There. What calculation will tell me that little red angle? Well, an entire circle is 360 degrees, and I want the red part, so I want to take all of this black angle away. The black angle is 300 degrees. Okay, the better way to do this though is to work in radians. 360 degrees is 2 pi radians. 300 degrees is 5 pi by 3. If I'm going to make a common denominator of 3, I need to multiply the 2 by 3. I can now go 6 minus 5 is 1 pi by 3. Now it must be important because I've written it twice. If the question starts in radians, you must answer in radians. That's so important. The next couple slides, I'm jumping over because we've decided not to do these in COVID-19 learning. So that brings us to the last slide where it has your textbook questions. Now, pay attention. You only have to do part of these. Since we got rid of the last two slides, you don't have to do 12AB, 13, 14, and 16. I need you to omit these because of COVID. If you have any questions or you'd like to see the solutions drawn out, I can quickly do them on the whiteboard and send you a picture. Just send me a quick email.